On the morning of July 21st, 1969, Neil Armstrong climbed down the ladder of the Eagle lunar module and stepped onto the surface of the moon. He planted a flag, he spoke his famous line, he took photographs. Then he reached into the pocket of his spacesuit and pulled out a Fisher space pen, a pressurized ballpoint that had cost NASA approximately $6 per unit, and wrote notes on a checklist strapped to his wrist. In Moscow, Soviet engineers and cosmonauts read the reports coming in from Apollo 11. They had beaten the Americans to nearly every milestone in the first decade of the space race. First satellite, first man in orbit, first spacewalk, first woman in space. They had done it with genius, courage, and sacrifice. But in the months that followed Apollo 11, something nagged at the Soviet space program's technical leadership. Something small, something almost embarrassing to admit. Their cosmonauts were writing in space with pencils. You might think that is a trivial detail, a joke even. You have probably heard the old story. NASA spent $1 million developing a pen that could write in zero gravity, and the Soviets just used pencils. It is one of the most repeated punchlines in the history of engineering. It shows up in management seminars, in comedy sketches, in corporate presentations about overcomplicated solutions to simple problems. It is also almost entirely wrong. And what actually happened? The real story behind who built the pen, how they built it, why NASA wanted it, and what it quietly revealed about the industrial systems competing for the future of humanity is far stranger, far more consequential, and far more instructive than the joke. Because this story is not really about a pen. It is about what a pen tells you, about who you are, about how you build things, about whether, when it matters most, your parts fit together, or have to be filed down until they do. The problem with pencils. To understand why a pen mattered in space, you have to understand what a pencil does in zero gravity. A pencil writes by depositing microscopic particles of graphite onto a surface. In Earth's gravity, those particles fall away harmlessly. In a sealed spacecraft cabin with no gravity and a recirculating oxygen atmosphere, those particles float. They drift. They work their way into instrument panels, into ventilation filters, into the gap between a relay contact and its housing. Graphite conducts electricity. A floating graphite particle in the wrong place is a potential short circuit. In a pure oxygen environment, which is what the early American and Soviet capsules used, a short circuit is a fire. On January 27, 1967, Apollo 1 caught fire on the launch pad during a routine test. 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee, died in the flames. The fire started from an electrical spark. The investigation that followed examined everything inside that capsule with forensic intensity. Every material, every component, every object that could contribute to ignition or combustion in a pure oxygen environment was reconsidered. Pencils were not the cause of the Apollo 1 fire, but in the aftermath, NASA's engineers were not interested in theoretical risks. They wanted a writing instrument that produced no particles, no flammable debris, no conductive fragments. They wanted something that would work in vacuum, in extreme cold, in extreme heat, at any angle, including upside down. Standard ballpoint pens relied on gravity to pull ink toward the tip. In zero gravity, they ran dry within seconds. Paul Fisher and the cartridge that NASA did not pay for. Paul C. Fisher was not an aerospace engineer. He was not a defense contractor. He was a pen maker from Boulder City, Nevada. who had spent the 1950s running the Fisher Pen Company and thinking, with what most of his competitors considered obsessive intensity, about the mechanical problems of ink delivery. A standard ballpoint pen uses a brass cartridge filled with ink at roughly atmospheric pressure. Gravity pulls the ink down against a small tungsten carbide ball at the tip, which rotates as it moves across paper, depositing ink. The system is elegant and cheap. It also fails immediately when gravity disappears, when pressure changes, when temperature drops below freezing, or when the cartridge is held at an angle that pulls air against the tip. Fisher's insight was conceptually simple and technically brutal to execute. Pressurize the cartridge itself. Instead of relying on gravity, use compressed nitrogen at about 35 pounds per square inch to force the ink toward the tip regardless of orientation, regardless of gravity, regardless of temperature. Seal the cartridge so that it could function in vacuum. Use a thixotropic ink, a substance that behaves as a semi-solid under no stress, but flows freely under the shear stress applied by the rolling ball, so the ink would not leak under pressure, but would write smoothly on contact. Fisher spent approximately $1 million of his own money developing this cartridge over several years. He applied for patents, he tested prototypes, he threw out failures. This is the origin of the NASA spent $1 million story, except that NASA spent nothing. Fisher spent the million. He then approached NASA with a finished product, sold the AG-7 anti-gravity space pen to the agency at $6 per unit, and eventually sold a version to the Soviet space program as well. The Soviets, it turned out, also wanted a pen that did not shed particles or rely on gravity. They had simply been waiting for someone to build one. The myth collapsed under basic research, but something more interesting remained once the myth was cleared away. Why one country built it and the other did not? To understand why Paul Fisher existed, why an American civilian pen manufacturer was capable of spending $1 million private dollars on an aerospace-grade writing instrument and bringing it to a finished, manufacturable product, you have to go back, as with so many things in the Cold War, to the structure of the two industrial systems competing against each other. The Soviet industrial model was a command economy built on centralized allocation of resources and centralized setting of specifications. A factory in Novosibirsk produced what the Central Planning Authority in Moscow told it to produce, at the quantities and specifications Moscow set, for delivery to customers Moscow designated. The system had genuine strengths. It could mobilize enormous resources toward a defined goal with remarkable speed. The T-34 tank, the MiG-15, Sputnik, Vostok. These were real achievements, produced by a system that could concentrate national effort the way a lens concentrates light. But the same system had a structural weakness that its planners never fully solved, and that weakness will be familiar to anyone who has read about German tank production in World War II: tolerance and interchangeability. The Soviet industrial system, like the German industrial system before it, was built around the skilled worker, the master machinist, the craftsman who could take two components that did not quite fit and make them fit through experience and manual adjustment. The gauge tradition, the American system of manufacturers, the idea that a part should be made to a standard tight enough that it simply drops in without filing. This tradition had roots in the Soviet system, but it never fully dominated the shop floor the way it dominated American production. This mattered enormously in the space race, though not for the reasons usually discussed. The usual narrative of the space race focuses on rockets, on launch vehicles, on the engineering of capsules and guidance systems, and those things mattered. But underneath all of it ran a quieter competition, the competition between two manufacturing philosophies, two ways of building the thousands of components that a spacecraft requires, two answers to the question of what happens when a part fails and needs to be replaced 400 kilometers above the Earth. The supply chain behind the moonshot. The Saturn V rocket that carried Apollo 11 to the moon was assembled from approximately 3 million individual parts. Those parts were manufactured by some 20,000 companies and 400,000 workers across the United States. They were made in machine shops in Ohio, in electronics plants in California, in rubber fabrication facilities in Michigan, in specialty chemical plants in New Jersey. They arrived at assembly facilities in Florida and were fitted together with a tolerance that made the entire stack function as a single integrated machine. The man most responsible for the American manufacturing philosophy embedded in that supply chain was not a NASA administrator or a rocket engineer. He was a mechanical engineer from the Midwest named Charles Stark Draper, who had spent the 1940s and 1950s at MIT developing inertial guidance systems and, more broadly, pushing American manufacturing toward a culture of measurable precision. But the infrastructure Draper's work depended on, the machine tools, the gauge standards, the supplier qualification processes, the rejection of parts that failed specification, had been built over more than a century. It had been built by the Federal Armories at Springfield and Harper's Ferry in the early 19th century. It had been refined by Samuel Colt and Robbins and Lawrence, exhibited to astonished British observers at the Crystal Palace in 1851. It had been industrialized by Henry Ford at Highland Park in 1913. It had been enforced by William Knudsen during World War II, when Knudsen walked into plants across America and confiscated hammers and files and told suppliers that a part which did not pass the gauge was not a part, it was scrap. That inheritance, 150 years of building the habit of precision into the bones of American industry, is what made it possible for 20,000 companies to build 3 million parts that fit together well enough to carry 3 men to the moon and bring them back. The Fisher Space Pen was a tiny expression of the same inheritance. A private manufacturer, operating in a competitive market, had identified a technical problem and solved it to a measurable standard. The product either worked in vacuum at minus 30 degrees Celsius or it did not. There was no filing, no adjusting, no craftsman at the bench who could make it work by feel. It worked because it was built to work. The Soviet space pen problem was actually the Soviet chip problem. The Soviets eventually bought Fisher Space Pens. That transaction is often cited as a cute footnote, the enemy buying an American product. What it actually represented was something more sobering, an acknowledgement that the Soviet industrial system could not produce an equivalent. This was not an isolated case. Through the 1960s and into the 1970s, as the Cold War competition shifted from rockets and bombs toward electronics and computing, the same structural weakness that had prevented Soviet industry from building a reliable space pen began to manifest in far more consequential domains. In 1958, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently invented the integrated circuit, the microchip. By 1961, American defense contractors were using early integrated circuits in the Minuteman II missile guidance system, placing a national security premium on the manufacture of reliable, miniaturized electronics. The Pentagon became the primary customer and quality enforcer for a generation of American semiconductor manufacturers, driving them toward the same culture of measurable precision that the armories had driven into the machine tool industry a century earlier. The Soviet response to the integrated circuit was to copy it Literally. Soviet intelligence obtained American chip designs, and Soviet factories reproduced them. But reproducing a design and manufacturing it to a consistent standard are two entirely different problems. Soviet chip fabrication plants in the 1960s and 1970s produced chips with defect rates that American manufacturers would have considered catastrophic. The skilled worker could be taught to assemble a piece of equipment from defective chips, testing and discarding until a working combination was found. But you cannot build a modern computer industry or a modern military on craftsman's selection of functional chips from a sea of failures. By the late 1970s, the CIA's assessments of Soviet industrial capability, many of which were declassified after the Cold War ended, were noting with increasing alarm that Soviet microelectronics manufacturing trailed American capability not by months or years, but by entire generations of process technology. The Soviets could build individual components of impressive sophistication. They could not manufacture them in volume at the yields that modern military systems required. The war that was won before it was fought. In November 1982, Yuri Andropov became General Secretary of the Soviet Union. He was a former KGB chief, one of the sharpest analysts the Soviet system had produced, and a man who understood better than most of his colleagues the structural problems eating at the foundations of Soviet power. One of the first intelligence assessments placed on his desk was a comprehensive survey of the Soviet economy's technological gap with the West. The report's conclusions, reconstructed from later Soviet archives, were not optimistic. Soviet military hardware, the tanks, the aircraft, the missiles, remained formidable on paper, but the electronics inside that hardware were falling behind. The guidance systems in Soviet ICBMs were less accurate than their American equivalents. The radar systems in Soviet fighters were generating so much noise that pilots routinely flew with them switched off. The communications infrastructure of the Soviet military was so dependent on landlines that it was vulnerable to conventional interdiction. And underneath all of these specific failures lay the same cause. Soviet industry could not manufacture precision electronic components to the tolerances that modern weapons required, in the volumes that modern arsenals demanded, with the reliability that modern warfare assumed. Meanwhile, in California's Santa Clara Valley, something was happening that the Soviet planners had no framework to fully understand. The semiconductor industry was not just growing, it was compounding. Intel's Gordon Moore had observed in 1965 that the number of transistors on a chip doubled approximately every 2 years. This was not a law of physics. It was a law of manufacturing improvement, of engineers and process chemists and equipment designers relentlessly pushing the gauge tradition to its logical extreme, finding ways to hold tolerances at scales invisible to the human eye, building measurement instruments to enforce those tolerances, and competing in a market that rewarded the manufacturer who could hold the tightest spec at the lowest cost. The Soviet system had no equivalent driver. A Soviet semiconductor factory did not compete for customers. It fulfilled a plan. If the plan said produce 10,000 chips and 8,000 of them were defective, the factory had produced 10,000 chips. The skilled workers and engineers who could have identified the sources of defects and driven yields upward had no institutional incentive to do so. Improvement was not rewarded. The plan was. The stealth bomber and the abacus. In 1977, the Carter administration authorized the development of what would become the B-2 Spirit stealth bomber. The aircraft was a classified program, known only to a handful of contractors and officials, built around a central premise: that a bomber with a radar cross-section the size of a large bird could penetrate Soviet air defenses and deliver nuclear weapons before those defenses could respond. The B-2 required manufacturing tolerances that had never been attempted on an aircraft of its size. The radar-absorbing materials that gave the aircraft its stealth properties had to be applied to the airframe with a consistency measured in thousandths of an inch. Any gap, any surface irregularity, any deviation from specification would create a radar return that would betray the aircraft's presence. Northrop's engineers developed new fabrication techniques, new measurement systems, new quality control processes to hold those tolerances across an aircraft with a 172-foot wingspan. The Soviets knew, in broad outline, that American stealth technology was being developed. Their intelligence services had collected enough information to understand the concept. What they could not do was replicate the manufacturing processes that made stealth practical. They built radar-absorbing material. They could not apply it consistently enough to produce a meaningful reduction in radar cross-section at operational scale. The gap was not in scientific understanding. It was in manufacturing culture, in whether the workers on the shop floor had been trained for generations to hold a tolerance because the gauge said so, rather than because it felt right. By 1983, when Ronald Reagan announced the Strategic Defense Initiative, the missile defense program that the press quickly labeled Star Wars, the Soviet military establishment understood that they faced a choice. They could attempt to match SDI by building the computational and sensor infrastructure it required, or they could acknowledge that their industrial system was not capable of producing that infrastructure at the required quality and scale, and accept a strategic disadvantage that would compound with each passing year. They chose to negotiate. The arms reduction talks of the mid-1980s, the Intermediate Range Nuclear Forces Treaty of 1987, the strategic arms reductions that followed, these were not purely the product of goodwill or idealism. They were in significant measure the product of a Soviet leadership that had looked at its own industrial capacity, looked at the trajectory of American manufacturing technology, and concluded that the race was being lost on the factory floor. Gorbachev's engineers. Mikhail Gorbachev came to power in March 1985 with a clearer-eyed understanding of Soviet industrial failure than any of his predecessors had been willing to articulate in public. His economic reform program, Uskorenie, acceleration, was built on a diagnosis that Soviet industry was producing quantity at the expense of quality, that the skilled craftsman culture had produced workers who could make anything work by hand and nothing work by standard, and that this had left the Soviet economy structurally incapable of producing the consumer goods, the electronics, and the military hardware that a modern superpower required. The diagnosis was correct. The cure came too late. Soviet industry had been built from its inception under Stalin's 5-year plans around plan fulfillment rather than quality control. The incentive structure rewarded output. A factory manager who produced 100 tanks that each required 3 hours of field adjustment before the engine seated properly had fulfilled his plan. A factory manager who produced 95 tanks that dropped in on the first try had failed it. For 50 years, this system had selected against exactly the manufacturing culture that the gauge tradition embodied. You cannot fix that in 5 years. You cannot fix it in 10. The American gauge tradition took 150 years to build, from John Hall's workshop at Harper's Ferry in 1819 to the Saturn V launch in 1969. It was not built by decree. It was built by competition, by rejection of substandard parts, by the market's daily discipline of throwing out what did not fit and rewarding what did. A planned economy could copy the specifications. It could not copy the system that produced compliance with those specifications. What the pen actually tells you. The Fisher Space Pen is, by any objective measure, a trivial object. It writes, it works upside down, it functions in vacuum and at extreme temperatures. It costs a few dollars. Millions of them have been sold to civilians, to engineers, to outdoor enthusiasts, to people who simply like the weight of it in their hand. But the pen is also a data point in a very long argument. The argument is about what kind of industrial system produces reliable objects at scale. The American system, the system that produced the pen, the Saturn V, the Minuteman guidance chip, the stealth coating applied to the B-2 to tolerances measured in thousandths of an inch, was built on the idea that a part either meets the specification or it does not. And if it does not, it is discarded. Not adjusted, not filed, not assembled by a craftsman who knows how to make it work by feel. Discarded. This is a brutal philosophy. It wastes material. It demands investment in measurement infrastructure. It requires suppliers to meet standards that may seem, from the shop floor, almost impossibly tight. William Knudsen was not a popular man in the plants where he confiscated the hammers. The gauge inspectors who rejected parts were not beloved by the machinists who had spent hours producing them. But the philosophy compounded. Each generation of manufacturers built on tighter tolerances than the last. Each generation of measurement tools enabled tighter specifications. Each generation of competition drove yields higher and defect rates lower. The semiconductor industry did not achieve billion transistor chips through inspiration. It achieved them through the relentless institutionalization of precision. The same precision that John Hall was reaching for in his workshop 2 centuries earlier, trying to build a rifle whose parts could be freely exchanged. The Soviet system had brilliant engineers. It had courageous scientists. It produced genuine breakthroughs in rocketry, in material science, in mathematics. Sergei Korolev, the chief designer of the Soviet space program, was as gifted an engineer as the 20th century produced. But Korolev worked in a system that could build him a rocket and could not always build him a reliable transistor. His launch vehicles were hand-fitted by skilled workers who knew their machines the way a surgeon knows a patient, individually, intuitively, by accumulated experience rather than interchangeable specification. That worked for rockets in the 1950s. It did not work for microchips in the 1970s, and it could not work for the software-defined weapon systems, the precision-guided munitions, the satellite constellations that were beginning to define military power in the 1980s. The Cold War's decisive theater was not Germany or Cuba or Vietnam. It was the semiconductor fabrication plant. The part that did not need him. In November 1989, the Berlin Wall came down. 2 years later, on December 25, 1991, Mikhail Gorbachev signed the papers that dissolved the Soviet Union. The Cold War ended, not with a nuclear exchange, but with an acknowledgement, written in the bankruptcy of Soviet industry, in the empty shelves of Soviet stores, in the declining reliability of Soviet military hardware, that one industrial system had been right about something fundamental and the other had been wrong. There is an image that stays with me from the reporting on Soviet military equipment after the Cold War ended, when Western analysts were finally given access to inspect the hardware they had spent 40 years planning to fight. Analyst after analyst described the same experience, opening the access panels of Soviet aircraft, Soviet missiles, Soviet armored vehicles, and finding inside them evidence of hand-fitting, shims inserted to take up gaps between components that should have been dimensioned to fit, markings showing that a specific part had been assigned to a specific vehicle because it fit that vehicle and might not fit another. the skilled craftsman's signature everywhere.
It was impressive work, in a way. The craftsmen who had built and maintained those machines were genuinely skilled. They had made imprecise components function by knowing them individually, the way a pianist knows the particular resistance of a specific instrument's keys. But you cannot scale a piano technician. You cannot build a modern military by assigning a craftsman to every tank, every missile, every aircraft, every transistor. The Americans had understood this since 1819. They had built an entire civilization's industrial culture on the proposition that the part should be made right the first time, to a standard tight enough that it simply drops into place. Whether the place is a Springfield rifle, a Ford Model T, a Sherman tank engine in a Normandy field, a Saturn V rocket on Launch Complex 39, or a Fisher space pen in the spacesuit pocket of a man standing on the moon. Paul Fisher spent $1 million and several years of his life solving a problem that the American manufacturing system had equipped him to solve. Build a thing that works every time without adjustment to a specification that can be measured, verified, and reproduced. The Soviets wrote with pencils not because they were less clever or less brave, but because their industrial culture had never fully made peace with that requirement. The Fisher Space Pen is on display at the Museum of Modern Art in New York. It is in the permanent collection as an example of elegant design. It has also been to the moon. What it is most, though, is a $6 object that contains 150 years of industrial philosophy. The accumulated argument, made in rifle workshops and automobile plants and semiconductor fabs and aerospace supply chains, that the part which does not need the craftsman to make it fit is worth more than any craftsmanship in the world. The Cold War was fought with missiles and ideology and proxy wars and Olympic boycotts. It was decided on the shop floor.